Thank you very much, Darwin, for that introduction to the literature review and our methodology. As Darwin has said, my name is Vinh, and I'll be discussing the results and our findings in the context of this study. Now, from case one, as Darwin has highlighted earlier, we managed to ascertain the pressure distributions across the plates. Now, the purpose of this case one study initially is to verify our model and see whether the mesh and the chosen parameters are correct in accordance with past literature. The CP values increase, as you can see in here in the figures, can be seen to increase alongside the angles of attack. The more critical orientation can be seen for orientations B, where the strong pressure coefficients owed to uplift is seen to have a higher value for orientation B. The CP intensity and distributions differ in trend and magnitude between orientations A and B, particularly when the angle is greater than 20 degrees. It can be noted that the CP deviates quite significantly with angle of attack 25 degrees and 30 degrees, as you can see the trend holding to its own independent pressure distribution. Now, the modelling accuracy of the CP values can be less relied upon, as can be seen, as the angle of attack increases. This is what we found for the case one simulations. This is owed to the two-dimensional nature of this simulation, as observed also in the angle of attack 30 degrees conducted by Yang. Adopting the orientation B just like us, the deficiency of the two-dimensional simulation is shown as the angle of attack is increased to 30 degrees, which can be noted in his study at the underside of the plate as it deviates away from the rest of his findings. Just like in our orientation B, with angles of attack of 25 and 30 degrees, there's a slight deviation, which is owed to the two-dimensional flaw that we get from this study. It's nothing of consequence, but it is a point to note as we progress further into unsteady and transient flow simulations. With that note, in case two, conducting unsteady and transient flow simulations, can be seen that there are no characteristic evidence of carbon vortices. Those are the swirls that can be witnessed subsequently after the plate. So there were no carbon vortices. But the flow at the trailing edge and especially does influence the long attached flow from the leading edge, seen in orientation B particularly, which is also observed in Yang's study, which is encouraging. However, in orientation A, there's less of a relationship between the trailing edge and leading edge wake and flow, with the velocity contours ranging between 12 to 14 meters per second, diverging out into its own separate course, as you can see in the GIF animations. The long attachment of the flow across the plate in orientation B with a velocity of 6 to 8 meters falls in accordance with the same proportion as Yang's study as well, at the middle of the plate, as the velocity intensity is of the right magnitude according to previous studies. Now, diverging away from just pure observation, we also want to gauge the extent to which, gauge how close these flow simulations across the inclined flat plates is to vortex shedding and how close it is to developing vortices. And so with this, we managed to extract the data, a coefficient of lift forces with time, in order to find the dominant frequency that is present across the flows of various angles of both orientations. And so, as you can see, as we increase the angle of attack to 40 degrees, a clear some sort of relationship can be seen. And so with these plots that are plotted here, a fast Fourier transform is able to be conducted upon the lift forces, the coefficient of lift with time, to ascertain the dominant frequency. Now, from the oscillatory shedding frequency in the form of a frequency spectra presented in a form of a frequency spectra. We can note that at the angle of attack of 40 degrees, the shedding frequency Struhl value is 0.143, which is very similar to the value that was found in Fage and Johansson's of Struhl's value, which is 0.148. The angle 20 to 30 degrees is quite negligible, exhibits quite negligible frequencies due to the angle with the flow bypassing the plate at these angles entirely. Now, despite, like I said before, no clear vortices presenting itself through the observation of the flow, the parameters and the frequency spectrum calculations do reveal, however, a progressive development towards vortex development, which is encouraging. This suggests that there are other factors involved, and so with this important note, we took our case 2 study further by decreasing the Reynolds number through altering the inlet velocity of 10 meters per second to 2 meters per second. This helps us to understand the effect upon the Struhl value that the Reynolds number has upon the Struhl value, and it helps us reveal how close the conditions are for vortex development. Now, when we decrease the inlet velocity, the Struhl value is seen to increase, which conflicts with trends and studies conducted by Yang, but confirmed Zhang's transitional flow boundary study, as we can see that the Reynolds has a significant impact as the flow changes with a great exhibition of wake intensity, thus indicating that the flow is transitioning into a more complex state. Hence the reason why the Struhl value is increasing, which is not expected, as we would expect it to decrease. And so from observing the Reynolds and Struhl value relationship, varying the input velocity from 10 meters to 2 meters per second significantly increases the wake intensity inundation about the plate, as you can see across the images here. At the trailing and leading edges, the intensity of the velocity is increased. The wake intensity is also increased after the plate as well. The observation verifies Zhang's study, especially his frequency locking region study, with the angle of 40 degrees transitioning itself further to vortex development. Now, with this transition to varying the Reynolds number, the means to capture the flow vorticity does get a little bit more complicated, which is quite interesting because it reveals that how much of an influence the Reynolds number has upon this flow simulation. And just to conclude, just to summarize our findings, the mean pressure from case 1 distribution about an inclined flat plate is suitable enough to signify that the model and meshing strategy is capable and adequate to conduct flow simulations. Pressure distribution output as a result of modifying the angles of attack correlates with the past studies, which is good. Now, and despite no clear exhibition of vortices, moving on to case 2, that is unsteady and transient flow simulations, the resultant flow in the wake does, however, hold traits, despite no vortices present, that are derived from the relationship between the leading and trailing edges. So the relationship between the trailing and leading edges do still exist, despite no vortices developed, which is an encouraging sign that our model is, in fact, correct. Lift coefficient intensity and oscillatory behavior upon the plate becomes further apparent with the increase of angle of attack, and the governing frequency and Struhl's number is found at 10 meters per second, indicate the vortex development potential despite no clear exhibition of vortices. And adding to the study further, by adjusting the Reynolds number, it reveals that the Reynolds number determines the state and conditions of flow, we all know that, but the reduced inlet velocity generates a more disturbed wake, and it signifies its importance and role and how much it influences the CFD modelling strategies that we adopt, and how adequate the results are. And so this evokes, due to this discrepancy through adjusting the Reynolds number, evokes suggestions and alternative pathways for further research. Some further research that we have recommended include study simulations at significantly lower Reynolds number. This can optimize the process of identifying the vortices and vortex shedding. And perhaps a three-dimensional analysis can be also thrown in the mix as well. This helps to capture the plates, additional plates that should be added, as well as the gap studies, and its effects upon the wake and vortex induce vibrations collectively and individually. And also perhaps a wind tunnel experimentation is encouraged as it captures what is seen at Werribee. And then going back and further adding in added stiffnesses and structural response mechanisms of the plate will help enhance the model further. And just to also conclude, we'd just like to acknowledge our supervisors, Professor Liu Ai and Dr. Kwang Nguyen, who has helped us with the research context and study and writing the report, Raymond Limitano, who's helped us ascertain some of the results, and also Dr. Don Riddle, who has helped us with writing up the report suggestions throughout the tutorials. So I'd just like to express our gratitude. And thank you very much for listening. I'd just like to open up the floor now to if any of you guys have any questions